Hello class, welcome to this lesson on the chi-squared test. So we're using this test in order to test for variances or standard deviations. In the previous lesson, if you recall, we did the z-test for proportions, and in the other lessons we looked at the z-test for means and then the t-test for the means. So now we're going away from means and proportions and we're focusing on measures of spread such as variance or standard deviation. So as mentioned, we are doing a chi-square test, so that means we need the chi-square distribution. So real quick, doing a quick rundown of the chi-square distribution. Recall that the chi-square distribution is actually, if we look at it, it's a curve that looks that is not symmetric at all. It's sort of like this, where it's skewed to the right. So it's not like a bell curve where it's symmetric. It's actually skewed to the right. So, and it's a family of curves. So the type of curve that you have depends on what we call the degrees of freedom. So the chi-square distribution is a family of curves based on the degree of freedom. Now, generally, as the degree of freedom is increasing, this is going to look more and more, symmetric, but it's still going to be skewed right. So all chi-square values, and because, we're dealing with chi-square, these values are actually squared. So notice that these are the positive values and there are no negative values here. Notice I did not extend the curve to the negative side of the x-axis. It's only on the positive side of the x-axis. And that's because all the values are squared and therefore they're greater than or equal to 0. So there is no left side to this curve per se in this. So the area under each chi-square distribution is the same as it was for the normal distribution and for the t, and it's equal to 1. So if you were to add up the entire area under the curve, it would just be 1. The chi-square distributions, as we mentioned earlier, they're not symmetric at all. They're positively skewed, otherwise known as skewed to the right. Okay, so that's just a quick summary, a quick rundown of the chi-square distribution. We did talk about that in another chapter when we did the confidence intervals, but just a quick rundown of what that is. So in order to look this up, in order to find like chi-square values, we're going to use the chi-square distribution table. So that's a very common table, but the table that I will use is a table that is from the book, which is this. So that's the chi-square distribution table that I'll use. So recall that this table right here, the chi-square distribution table, gives us areas to the right. So if you look at this, it's giving us an area to the right of the tail, which means that we're going to have to make adjustments. Okay, so if you recall in the other tables, they gave you an area to the left. So if we look at the standard normal distribution, it always gave you an area to the left. However, it's changed. They switched it up on us, and that's because it's positively skewed. So therefore, they ended up giving us areas to the right instead. So now because of that, we just have to be careful when we look up values. So whereas the standard normal distribution, we said that the standard normal distribution gives us areas to the left. So just a quick review of that. All right, so we're going to practice finding critical values using the table first. So we want to find the critical chi-square value for 15 degrees of freedom when alpha is equal to 0.05 and the test is right-tailed. Now, before we actually do the problem, let me just let you know right now that the formula for the degree of freedom is the sample size take away 1. In this case, we don't have to calculate it because they gave us a degree of freedom. But in case they give you the sample size and you need to get the DF, this is what you would use. All right, so now that they give us the degrees of freedom and the alpha, they also gave us that it's a right-tailed test. So since the test is right-tailed, what we do is I'm going to just quickly draw a curve, just a generic chi-square distribution curve here. So there's my curve. Now, since we are looking at a right-tailed test, we are already looking at the area to the right. So we're already okay as far as the table is concerned, because recall that the table gives us the area to the right. So we need to look up some critical value such that, and let me change this up real quick. We need to look up a critical value, so we'll call that chi-square critical, such that the area to the right is 0.05 because we are doing a right-tailed test. So this area right here is alpha is 0.05. All right, so and then notice that we have our df is 15. So we're going to look this up on the table, and for an area of 0.05. So if we go into the table, we see that we have a degree of freedom of 15 in this row right here, and we're looking it up for an alpha is 0.05, and there's no adjustments that we need to make at all. So if we go to 15 and 0.05, we get a critical value of 24.996. So that's going to be our critical value for chi-square. All right, and that's the answer that we're looking for. Again, no adjustments were needed to be made because we are already looking for a right-tailed test, so therefore the area that is given is to the right according to the chi-square table, so no adjustments are made. Now if we go to number 2, they specifically say that the test is left-tailed, so therefore we need to make some adjustments because the table gives us the area to the right. So they give us that the df is 10 and alpha is 0.05. So I'm just going to draw a generic chi-square curve. And we know that we're looking for, the area to the left being 0.05. So that means we're somewhere on this side of the curve where the area to the left is 0.05. So we need to figure out what this chi-square curve is. But remember that the table gives us the area to the right. So what we have to do is we really have to look up 0.95 on the table, because the table only gives us the area to the right, so we need to look this up for the chi-square. So if we go to the table, we're going to look up df of 10 and an alpha of 0.95. So we're on this side of the table. So we got 10 and 0.95, so our chi-square is 3.94. So that was the adjustment that needed to be made. So we get chi-square is 3.940. And notice that this value makes sense because this value right here is 0 at the origin, and we're only 3 off from that origin. So we're not very far from the origin, whereas in the other problem, we were pretty far from the origin, and therefore we got a chi-square of 24. So this makes sense. So now we're going to go to the third one. This time we're looking at a two-tailed test. So with a df of 22. So again, since we're doing a two-tailed test, what we need to do is we need to split the alpha amongst two tails. So we need to do alpha divided by 2, which is 0.025. So this means that we have two chi-square values because it's a two-tailed test. In the left side, and the left tail is worth 0.025, and the right tail is also worth 0.025, as we calculated here. So now we're looking for two chi-square values, one on the left, one on the right. So if we want to find the chi-squared value on this left side, what we need to do is we need to look up the area 1 minus 0.025. And that's because the table gives us the area only to the right, and we're looking for the left here. So therefore, we're going to look up 0.975 for the left critical value. Now for the right critical value, we already know the area to the right of 0.025, so we can simply look this up and we don't have to make any adjustments at all. So we're going to the chi-square table for a degree of freedom of 22, And as we mentioned earlier, we need to look up 0.975 for the left critical value and 0.025 for the right critical value. So if we look up 0.975, then for a degree of freedom of 22, that's 10.982. And then on the right side, for 0.025, we have a critical value of 36.781. All right, so we said that this was 10.981 for the left side and 36.781 for the right. Let me double check that left value. This was 982. Let me double check it again just to make sure. Yes, so 982 and 781. So we got our two critical values, and they make sense because we have 10. We're only 10 away from the origin, whereas here we're 36 away from the origin, so we're on the right side. All right, so we got our two critical values, and so that is, those two are our answer. So again, with the other lessons, we've always had a plus or minus for the critical values. This time we're not going to have critical values. We can never get negatives from chi-squared. All right, so we're going to, next up is the test value for the chi-squared. So this is the formula for the test value. Again, this is important to have a test value formula because we need to compare this to the critical value to determine if we reject or not. So this is the formula that we use. So recall that the S squared is the sample variance and the sigma squared is the population variance. All right, so there are some assumptions that need to be made for the chi-squared test. The first assumption, just like with any other test, is that the sample must be randomly selected from the population. This is the case for all the tests that we have discussed so far. For the second assumption, we have to assume that the population is normally distributed for the variable under study, which is usually have been the case for the other studies as well, the other tests. In addition, the observations must be independent of one another, so there must be no dependence among the observations. So if I make one observation, it should be completely different or independent of another observation. So now we're going to discuss the traditional and the p-value methods when we do the problems. So remember that we had the two ways to perform a hypothesis test, and these methods are going to have the same steps for the chi-square, except for the change in the formula and using the chi-square table. So we're going to show you how to find the p-values now. So if we want to find the p-values, recall that we need to use the chi-square table for the chi-square test. So notice that the chi-square table here, there's no way of getting an exact p-value unless you get one of these values in the table. So most of the time, you're not going to have an exact p-value. You're going to be given a range of p-values that you need to find. So therefore, we're going to be looking for a range of values here. So therefore, our job is to find the interval or range of p-values. So we need to first find the degree of freedom, df, which is n-1, as we mentioned earlier. Now for a right-tailed test, what we do is we look up the df, and in that row, we look up the given test value. We want to get as close as we can to the test value, and then if it is between those two numbers, we find the two values of alpha that correspond to it. So for example, if my df is 12, and I'm looking at a test value of 4, then 4 is between those two numbers. And so we want to look at a right-tailed test. So let's look at another example. So if the df is 12 and we're looking at a right-tailed test of like 22 for our test value, then we want in between 21 and 23 here. So therefore we look this up, and so our p-value is between those two numbers, 0.05 and 0.025. Now if we're doing a left-tailed test, it's a little bit different. What we do is we repeat the step for the right-tailed test, but then we have to subtract from 1 to get the area. So for example, the example that I was about to give you to begin with, if we have a degree of freedom of 12 and I give you a test value of 4, Well, 4 is between 3 and 3.57 and 4.4. So therefore, our p-value is between those two. However, because we're looking at the left side, we need to subtract those from 1. So this will be 0.01 and 0.025. For a two-tailed test, if you're on the left side of the table, you need to subtract the alpha values from 1 and then double the values. If you are on the right side, just use the alpha values and double them. So for example, if I give you a degree of freedom of 10, and I said that the test value was 19, then if we look at the table, well, 19 is between 18.3 and 20, and therefore, and we are on the right side of the table, so we are going to look up these values here, 0.05, 0.025, and then we double those values. So then we got a double 0.05 and then double 0.025, and then our p-value is between those two doubled values. If we are on the left side for a degree of freedom of 10, such as if we have a test value of 3, then we are between these two numbers, and therefore the p-value is between those two numbers. However, we need to subtract those two numbers from 1, so this will give us 0.01 and then 0.025. And then we double those values to get the new p-value. All right, so I know this seems a little, seems like a lot, but we're going to do a couple of problems. So if we look at this problem here, number 4, so we're going to practice finding the p-value. So if we look at this one, this says that the chi-square, or the test value, is 19.274. So this right here is the test value that I mentioned earlier. And we got a sample size of 8, which means that we need to find our df. So our df is 8 minus 1, or 7. This time we're looking at a right-tailed test. So we're going to look up this 7, and then we're going to get as close to 19.274 as possible. So the degree of freedom of 7, 19.274, is between these two values. So therefore my p-value is between these two values. And I don't need to make any adjustments since I'm looking at a right-tailed test. So my p-value is between 0.005 and 0.01. Remember that the smaller number goes first in the interval. So these are my range of p-values. So for number 5, we're doing a left-tailed test, and we have a degree of freedom of 12. And this is our test value that we need to look up. So we need to get as close to that test value as possible for a degree of freedom of 12. So if we go to a degree of freedom of 12, we want to get as close to 3.823 as possible. So that is between these two numbers. All right, and then for a degree of freedom of 12, we have those two numbers there. Now this means our p-value is between those two numbers. However, since we're doing a left-tailed test, we need to subtract these numbers from 1. So if we subtract 0.99 from 1, we get 0.01. So I'm going to write these two values down on the notes, and then we're going to subtract them from 1. So we got 0.99 and 0.975. So we're going to go ahead and subtract those from 1. So I'm going to do 1 minus this and 1 minus that. And so now we get 0.025 for this guy. So this is now 0.025, and this is 0.01. So now our p-value has to be between those two numbers. However, you want the smaller number first and then the larger number second. So this works out nicely. So we have a p-value between 0.01 and 0.025. All right, so now what we're going to do is we're going to do a two-tailed test with a degree of freedom of 12, same as it was in the previous problem. Same test value, but this time it's two-tailed. So then, since we're doing the same value, 3.823, and the degree of freedom of 12, this means we have the same values, 0.99, 0.975. So since we are on the left side of the table, we subtract from 1, and we get our new values. Then we double them because we're doing a two-tailed test. All right, so we have to do 1 minus 0.99 and then 1 minus 0.975, and then we have to double it because we're looking at a two-tailed test. All right, so basically we got a double 0.01, and that gives us 0.02, and we got a double 0.025, which gives us 0.05. So therefore our p-value is between those two numbers. All right, so that's how you find the p-value for the three methods. Again, for the left side, you simply look up the p-value and you don't have to make any adjustments. For the right side, and then for the left-tailed test, you simply look up the value as you would for the right-tailed, but then subtract from 1. For the two-tailed test, you look it up as you would any other test, but then if you're on the left side of the table, subtract from 1. If you're on the right side of the table, do not subtract from 1. Regardless of which case you're doing, you're going to double the final result to get your final p-value. All right, so we're going to look at a problem where we used the traditional and the p-value methods. So note that we're going to be using both methods in this lesson to get you accustomed to both critical values and p-values. So the standard deviation for the math SAT test is 100. The variance is 10,000. An instructor wishes to see if the variance of the 23 randomly selected students in her school is less than 10,000. The variance for the 23 test scores is 7225. Is there enough evidence to support the claim that the variance of the students in her school is less than 10,000 at alpha equals 0.05? So again, the first step in any hypothesis testing process is to identify your claim and your hypotheses. So we have our null hypothesis and our alternative hypothesis, just as it was in the other lessons. So now they said that we want to support the claim that the variance is less than 10,000. So again, the symbol for the population variance is sigma squared. If they're asking about standard deviation, we would just simply use regular sigma and not sigma squared. All right, so they want to test a claim that the variance is less than 10,000. So since it's less than, that belongs to the alternative, since the alternative is a statement of inequality. The null is a statement of equality, and so we're going to say that this is either greater than or equal to, the direct opposite, or we could say equal to, and we'll be fine. So since it's less than 10,000, we said that this is our claim, and since it is less than, this means that it is a left-tailed test. So again, just to remind you, the type of test depends on the alternative hypothesis. If it's less than, it's left-tailed. If it's greater than, it's right-tailed. If it's not equal to, it's two-tailed. All right, so now that we got the hypotheses set up, we're going to move on to step 2, which is to find the critical value. So to find the critical value, this is where we use the ChiSquared table. So since we're doing a left-tailed test, and we have our alpha is 0.05, and we need to find our DF here. So our degree of freedom is, so they said that they selected 23 test scores, so therefore our N is 23. So this means that our degree of freedom is 23 minus 1, or 22. So we're looking at 22 degrees of freedom for an alpha of 0.05. So again, if we quickly draw the chi-square distribution table, just to help us with our critical value, since we're doing a left-tailed test, that means the area to the left is 0.05, which means we need to find the area to the right because the table gives us the area to the right. So we need to look up 1 minus 0.05, which is 0.95. So we need to look up 0.95 on the table to find our chi-squared value. So if we go to the table, we got 22 degrees of freedom and an alpha of 0.975. So which means our critical value is 10.982. All right, so now we got the critical value for the left tail test. So that's over here, 10.982. So now we need to find the test value. So to find the test value, we use the formula that was given earlier in blue in this area. So we got the test value, which is n minus 1 s squared over sigma squared. So this will be our chi-squared test. Over sigma squared. All right, so I went ahead and I plugged in the numbers into the formula. So the n is 23, so we did 23 minus 1. The s squared is the sample variance. So if we go up to the problem, it said that the variance for the 23 test scores is 7225. So we said that that was our sample variance. And then our sigma squared is simply the 10,000 from our claim here. So from our claim. So we went ahead and plugged it in. We got the test score of 15.895. So now what we're going to do is we're going to label that test score on this graph, the graph that we did up here. So if we label it on here, then the 15.895 is somewhere in here. All right, so since we are, so this right here that this graph that this tail that I shaded, this is our rejection region. So therefore we are outside our rejection region, which means that we fail to reject here. So our decision is we're going to fail to reject the null hypothesis. All right, so step 5 is going to be our summary. Since we failed to reject, that means we don't have enough evidence. So we're going to say there is insufficient evidence at the, and then we were looking at the 5% level. So there is insufficient evidence at the 5% level of significance, LOS. 2, now since our claim belongs to our alternative, this means that we're going to use the word support instead of reject. So there is insufficient evidence to support the claim. And then if you go to the problem, the claim was that the variance is less than 10,000. So claim that the variance is less than 10,000. All right, so that's the traditional method. So if we look at the p-value method, the step 1 is identical. So I'm going to just say that it's the exact same thing. So we just repeat what we did in traditional method. For the p-value method for step 2, we need to find the test value, which we already did in step 3. So I will just repeat what the test value is here. So which is 15.895. Step 3 for the p-value method is to actually find the p-value. So in order to find the p-value, recall that since we're doing a left-tailed test, we're going to look up the values from the table and then subtract 1 and subtract those values from 1 to get the p-value. So we're going to get as close to 15.895 as possible with a degree of freedom of 22. And then get our values. So 15.895 and 22. So 22 degrees of freedom, 15.895 is between Let's see. All right, so then if we go and we look up the value, so let me just show you. So let's go back to the table. So if we have a chi-square test of 15.895 with a degree of freedom of 22, well, notice that we're between those two values. However, we're going to do a snapshot so that we can show you what we're looking at here. So if we look at here, we have a degree of freedom of 22, and we're here, right? Here, between here and here. However, this right here is the halfway point for the table. So like everything here is to the left. This is the left side, and then this right here is the right side, right? Which is why the values change from 0.9 to 0.10. So this means that our 15 value is somewhere around here. So we're somewhere here between the 14 and in the middle of the distribution. So what that's saying is that we're somewhere here as far as the alpha or p-value is concerned. Now, since we are looking at a one-tailed or a left-tailed test, this means that we need to subtract these from 1, right? So this right here will now be 0.10 because 1 minus 0.9 is 0.10. So let me just rewrite this here. So this is 0.10, and therefore, here, let me try this again. So this right here will be 0.10, and this right here will be 0.05 if you do 1 minus. So notice that the numbers are getting larger as we go to the right. This means that my p-value is only going to get larger than 0.10. So therefore, we can safely say that the p-value is greater than 0.10 here. So this is one of those weird cases that you just have to think about it a little bit. And so we are definitely going to be greater than 0.10, but we're not sure by how large. So we're going back to the problem, we're going to say that the p-value is greater than 0.10, which if you compare that to our alpha, remember that if the p-value is greater than alpha, you fail to reject. So being greater than 0.10 is clearly going to be greater than 0.05, so therefore we fail to reject. And therefore step 5 is the same. Okay, so I wanted to go over that problem because sometimes you'll come across a scenario where it's not between two values per se, and you have to kind of figure out, what the p-value is going to be. All right, so for number 8, we have a hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days is selected. The data are shown. At alpha equals 0.10, is there enough evidence to support the administrator's claim? Assume that the variable is normally distributed. All right, so clearly they don't give us the variance or the standard deviation or anything like that. They only give us the claim for the standard deviation. So they give us sigma, and they said that the sigma is greater than 8. So again, we're going to be looking at the two methods here. So we're going to look at traditional and p-value on one end. So let's look at the traditional. So step 1, we need our hypotheses. So they said that the claim was that the standard deviation is greater than 8. So since we're looking at greater than, that's an inequality. There's no equal sign at all. If it was greater than or equal to, it would belong to the null. But since it's greater than, it's the alternative. So this is saying that the standard deviation is sigma here, not sigma squared. Sigma squared is the variance. So this is saying that sigma is greater than 8. All right, so now that we got this is right here is our claim. So let me label that our claim. And since it's greater than 8, we're looking at a right-tailed test. And here we can say that it's either less than or equal to 8, or we can say it's equal to 8. And so that's our null. So now for step 2, we need to find the critical value. So again, since we're doing a right-tailed test, we only need to look up the value. We don't need to subtract from 1 or anything like that. So I'm going to go ahead and draw a generic distribution. First off, though, the alpha is 0.10 in my df. So if you look at the problem, it says, well, based on the data that we have here, we have about 15 subjects. So we have our n is equal to 15, which means our degree of freedom is 14. So we look up the degree of freedom of 14 with an alpha of 0.10. All right, so we're going to go to the table. With a degree of freedom of 14 and an alpha of 0.10. Now, since we're looking at a right-tailed test, we don't need to subtract from 1 at all, so we're just going to look at 0.10. And we have a test value, or a critical value of 21.064. So I'm going to draw out the curve just so that we can see what we're looking at here. So we're looking at a critical value of 21.064. And this area to the right, and we'll shade that in red because that'll be our rejection region, is 0.05 or 0.10, I'm sorry. So that's our alpha. All right, so now we got our critical value. So we need to, next up is our test value. So in order to find the test value, we're going to be using the formula. So for step 3, we need to use the formula for the test value, which, if you recall, is chi-squared left, or chi-squared test, I'm sorry. Chi-squared test is equal to n minus 1 s squared over sigma squared. So what we need to do is we need to plug in my n, s squared, and sigma squared. However, we need to find out what the standard deviation, what the variance squared is, and what the, well, we know what the sigma squared is, because we know that the sigma is 8. So that means that sigma squared is 64. But we need to find out what s squared is from the data here. So we're going to plug this into the calculator in order to get the s squared, and then plug it into the formula for the test value. All right, so I went ahead and I calculated the variance squared using an online calculator. You can also use a scientific calculator to find this. So the variance for this data given is 125.5. So that's this s squared that I found and I boxed up. Now that we have the s squared, I went ahead and I plugged it in to the formula. So we know that we had 15 numbers, take away 1, times the 125.5, which is the variance that I calculated earlier using the online calculator. And then the sigma squared, remember that the standard deviation was 8, so 8 squared gave us 64. So then plugging in those numbers, I got a chi-squared test of 27.453. So I'm going to label that on the curve that that was drawn. So that means that our test value is somewhere around here. So this is our 27.453. So that means we are inside our rejection region, which means we are going to reject the null hypothesis. So step 4, we reject the null hypothesis. So then when we write the summary, we have there is enough evidence and we're looking at a 10% level of significance. So at the 10% level of significance, our claim belongs to our alternative, so we're going to use the word support instead of reject. So to support the claim that, and then our claim from our problem was that the standard deviation is greater than 8. Standard deviation of people using outpatient surgery is greater than 8. So that the standard deviation of those using outpatient surgery is greater than 8. So we have our summary, so we're done with the problem. However, I'm going to show you the p-value method. So again, the p-value method is the same as the first step is the same as the traditional method. As far as the second step, we need to find the test value, which we can repeat from step 3 with the traditional method. So we got a chi-square of 27.453. So now we're going to calculate the p-value. So I'll do that. I'll actually do that down here. So if we do our p-value, so what we're going to do is we're going to look up the test value of 27.453. We're going to get as close to that test value as possible with a degree of freedom of 14. And then since we're doing a right tail test, we don't need to make any adjustments whatsoever. So 27.453 with a degree of freedom of 14. So degree of freedom of 14. Let me zoom in a little bit. And then we're looking at a test value of 27.453. So that's between these two numbers. Since we're doing a right tail test, we don't need to do anything with these two numbers. So that means our p-value is between 0.01 and 0.025. Alright, so p-value is between 0.01 and 0.025. Alright, so we got our p-value. So now we can make a decision. So now if you look at the range, if the p-value is between 0.01 and 0.025, and we want to compare it to the alpha, well, remember that the alpha is 0.10, so this is clearly less than 0.10. So this means that the p-value is less than 0.10, which is our alpha, so this means we reject. So if it's less than or equal to, we reject. So step 5 will be the same. Alright, go ahead and give this problem a try, and we'll go over what the solution is in a little bit. Alright, so let's go over the solution to the problem. So we got a cigarette manufacturer wishes to test the claim that the variance of the nicotine content of its cigarettes is 0.644. So we got a claim, and it says it is equal to 0.644. So this is my sigma squared. So we're going to use both methods. So the first step in the process is our hypothesis. So they said that the sigma squared is equal to, and equality belongs in the null hypothesis. And it says, is there enough evidence to reject the claim? So it doesn't say whether it's greater than or less than. So we will just say it's not equal to 0.644. This means that this is a two-tailed test. And here we're looking at the claim of 0.644. So now we got step one. Now step two is the critical value. So we need our DF. So it says a random sample of 20 cigarettes, so that's our N, has a standard deviation of 1 milligram. So again, they're trying to trick you with the standard deviation. So this right here is our S. So S is equal to 1, which means we need to do the sample variance, which is squaring it. But 1 squared is going to give us 1 anyways. So it won't really change the answer. However, if it wasn't 1, it would change your variance. So we got a degree of freedom of 20 minus 1, or 19. So since we are doing a two-tailed test, we need to remember to look up the value that we get, and then for the p-value, and then double it when we do the p-value. However, when we're doing the critical value, if we're doing the two-tailed test, we are looking for 2 critical values, and for an alpha, let's write down our alpha here. Our alpha, we need to take our alpha and divide it by 2. So we get 0.05 divided by 2. And that's because we're doing a two-tailed test. So this gives us 0.025. So we're going to draw our chi-square distribution so that we can see what we're looking at here. So we got a generic chi-square distribution. We have 2 critical values that we need to find. One on the left, one on the right. So the area on both sides is 0.025. And I'll do this in red because these are our rejection regions. So this is also 0.025. Now when we look up the chi-square critical on the left, remember that the chi-square distribution gives us the area on the right. So that means we need to do 1 minus 0.025. Which is 0.975. So when we look up the critical on the left, we need to look up 0.975. If we do the one on the right, well, we just need to look up 0.025 since that's the area on the right. All right, so going to the distribution, we need 0.025, 0.975, and a degree of freedom of 19. So degree of freedom of 19, and we need 0.975 for the left side, which is 8.907. And 0.025 for the right side, which is 32.852. So on the left side we got 8.907. So that's one of our criticals. And the other one's 32.852. All right, so we got our criticals. So now we need to find our test value, which means we need to calculate the chi-squared test. So again, the formula is n minus 1, so it's 20 minus 1 times s squared, and s squared is just 1, and then over sigma squared. So they said that sigma squared from the claim is 0.644. All right, so typing this in, or plugging this into the calculator, we get a test value of 29.50. So now we're going to label that on our chart, on our graph here. So that means we're somewhere on the right side, and I'm going to do it in blue. So we're somewhere here, 29.5. And so therefore, we can see that we are outside our rejection region, so therefore we fail to reject. So here we fail to reject the null hypothesis. All right, so since we failed to reject, this means we do not have enough evidence. In addition, the claim belonged to our null hypothesis, so we used the word reject. And our claim was that the variance is of the cigarettes, the variance of the nicotine content is 0.644. So we say that there is insufficient evidence at the 5% level of significance. So we're going to use the word reject to reject the claim that the variance of nicotine content is equal to 0.644. I believe that's what the number was. Yes. All right. So there is the traditional method. So now we're looking at the p-value method. So again, the first step is the same. Step 2, our test value, chi-squared, is 32.852. And then step 3, we're going to do our p-value. So we're going to look up the degree of freedom is 19, and we're going to get as close to this value as we can. Now, since we are doing a two-tailed test here, we're going to double the values that we get from the chart. So if we're on the left side of the chart, we subtract from 1 and then double it. If we're on the right side, we keep the number, but we double it. All right, so 32.852 and 19. So 19 and oh, I wrote down the wrong value here. Sorry, guys. So this is not our test value. Our test value was 29.50. There you go. So we're going to get as close to this value as we can. So 29.50 with a degree of freedom of 19. That means we're between those two numbers. So that means we are on the right side of the table. So that means we're between those two. And we don't need to subtract from 1 since we are on the right side. So therefore, our p-value is between those two numbers. But since we're doing a two-tailed test, we need to double those. Okay? So between 0.05 and 0.10. But we have to double them. So this means our p-value is between 0.10 and 0.20. So therefore, for our step 4, our p-value is clearly greater than alpha. So therefore, we fail to reject. So step 5 is the same. All right, so go ahead and try this problem. This will be the last problem of the lesson that we'll look at, and then we'll go over the solution. All right, so let's go ahead and try the problem. So we have a researcher knows from past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. A random sample of 24 cars is selected and inspected. The standard deviation is 12.5 minutes. Alpha is 0.05. Can it be concluded that the standard deviation has changed? Use the p-value method. Now it says use the p-value method, but yeah, we'll just use the p-value method. Or actually, I'll show you both methods just so that you can see both methods, since I've done the same thing the entire video. So we're gonna stick to doing both methods, even though it says use the p-value method. All right, so now we're going to I went ahead and did the problem just to save a little time, and so I'll just kind of do a walkthrough to the problem. So it says that the researcher knows that the standard deviation is 16.8. So that's why we said that sigma is equal to 16.8 for the null hypothesis. And we're going to do the direct opposite, which is not equal to for the alternative. Since it's not equal to, this means we're looking at a two-tailed test. Next, we find the critical value. So we need to find the df. So that's n minus 1, or 23. So it said in the problem, it said that we're looking at 24 cars, so that's our n. It also said that the standard deviation for the 24 cars is 12.5 minutes, so that's s. And then the 16.8 is our hypothesis, sigma. So since our df is 23 and our alpha, we're doing a two-tailed test, this means we need to divide alpha by 2, which gives us 0.025. So I went ahead and I drew my chi-square distribution and I labeled each area 0.025. So if I need to look up the critical value for the left side, I need to do 1 minus 0.025. So I need to look up 0.975. If I need to look up the right critical value, I simply look up 0.025. So if you go to the table for a degree of freedom of 23, for 0.975, our critical value is 11.689, which was the number that we got on the left. And then on the right side, we got 38.076 for a alpha of 0.025. So that's how I got those two values. Then I calculated the test value, so the chi-squared test. So n is 24, the s was 12.5, so I make sure to square that. And then the sigma is 16.8, so I squared that as well. And we got a test value of 12.7. So I went ahead and labeled the test value on the curve, and it's clearly outside the rejection region, so we failed to reject. So therefore, we do not have enough evidence, so we have insufficient evidence to reject the claim. We say reject because the claim belongs to our null. And then the claim that the standard deviation is 16.8. Then for the p-value, we repeat the step 1, and then step 2 is the chi-squared from step 3. For the third step, this is the part that I wanted to show you. Since the chi-square is 12.73 and we're doing a two-tailed test, we know that we need to double the values that we get. And if we are on the right side of the chart, we need to do 1 minus the values that we get. So we're going to get as close to 12.73 as possible with a degree of freedom of 23. So for a degree of freedom of 23, we need to get as close to 12.73 as possible. So notice that we are on the left side of the table. So if we're on the left side of the table, we look up the values and we subtract 1 from them. So we do 1 minus 0.975, 1 minus 0.95. Now, since we're doing a two-tailed test, we need to double those values once we subtract them from 1. So this is what I did here. I subtracted the values from 1, or I subtracted them from 1, and then I doubled them. So then I get this as my p-value. So clearly the p-value is greater than alpha, so therefore we fail to reject. Alright, and that concludes the lesson, guys. I hope that you found this useful. I know it was a long video, but there was a lot of problems to show you and a lot of methods. Alright guys, take care and have a good day.